Good morning, everybody, and welcome to our last week of statistics. Before I go on, we need to make sure that we are looking at Remind and getting that Google form I sent out this morning filled out. We need to schedule our final on Friday. Everybody has to take it during the same 2-hour window. That's a university policy. That's not me. So we have to come up with a agreed upon time in order to schedule this final. As of right now, 8 people have replied, and we are only we're currently looking at 12 to 2. So please make sure you're getting in your choice or your preferences for what time to take the final. Today we're looking at Way ANOVA testing. We're just going to look at the logic behind the testing. We're not actually going to set up or do the hypothesis test. We're going to do that tomorrow. ANOVA simply means analysis of variance. And when we're talking about the analysis of variance, in this particular case, we're comparing multiple population means. Whereas in the past, we've looked at 2 population means. Here we can look at more than 2. We can look at 3, 4, 5, however many population means exist for the purposes of our test. For example, let's take into consideration that our 4 populations might be the Northeast, the Midwest, the South, and the West. So those are our 4 populations that we may want to investigate. And the variable that we're looking at is the energy consumption in those 4 regions. So we would take samples from all 4 regions, establish their means, and then we would come up with this ANOVA test to compare their means. Comparing 2 means is easy. We've done that. Comparing multiple means is not as straightforward, so we have to look at a couple of different factors before we can proceed. So some of the assumptions that have to be met before we can conduct a Way ANOVA test: 1, that we have simple random samples; 2, that they are independent samples; 3, that we're looking at normal population or roughly normal populations; and then 4, that the standard deviations of all 4 populations, or their samples rather, are approximately equal. And comparing 2 sample standard deviations, easy enough. Comparing 4 is not as easy. So we have what we actually call the rule of 2. And the rule of 2 is if you have the ratio of the largest standard deviation divided by the smallest standard deviation from your samples, if that value is less than 2, then you can claim that all the standard deviations are approximately equal. If it's greater than 2, then you cannot make the claim that they have equal standard deviations, and the Way ANOVA test will not apply. I'm going to kind of skip over this logic behind the test right here, simply because we've looked at examples like this before where we compare 2 populations. They have different means. We're trying to establish whether or not their means are equal or not equal. In this first example, the way the spread is of the data, you cannot make the claim one way or another that the 2 means are equal or not equal. However, with the second set of data, they both have the same means as the prior example, but we can see how these values here are clustered around 20 and these values are clustered around 25 because the data is not as spread out. There's not a lot of variance in the data. So we can say that these 2 population means do differ based upon this graphical representation. That's not as easy to do when you have more than 2 populations, and that's why we have this ANOVA test. With the ANOVA test, we are going to introduce some new variables, but we're also going to reuse some old parameters and statistics that we should be familiar with. For example, right here, if we're talking about a population 1 for that matter, then we would have mu sub 1 is the population mean of population 1. X bar sub 1 would be the sample mean of population 1. S sub 1 is the sample standard deviation. And then N sub 1 would be the size of the sample that represents population 1. With the Way ANOVA test, we do have some new variables or new calculations that we have to come up with. The first one is the treatment mean square, which is abbreviated MSTR. That's the treatment mean square, and it's found by taking the treatment sum of squares, which is the SSTR, divided by K minus 1, where K is the number of populations that we are investigating. SSTR can be calculated by taking each individual or sample size times the difference in the sample mean and the overall mean of the population or the samples, the quantity squared, plus you repeat that process for each individual population. And to compute that, we're going to see that here on Google Sheets here in a minute. It's very easy if you use Google Sheets. If you use the formula, you have to be very, very careful about where you enter your values. Another value that we're going to have to compute is called the error mean square, which is MSE. And the error mean square is found by taking the error sum of squares, SSE, divided by the total number of observations minus the number of populations. And the way we compute SSE is the sample size for each individual population minus 1 times the variance for that particular population. And then finally, we would come up with the value for our F statistic, which is the MSTR divided by MSE. And this green box just abbreviates or condenses all that information into one little location for you to look at. But it's probably easier to put this into practice to try to understand it. So again, we're looking at the energy consumption for the 4 regions of the United States. And we have to first establish what our hypothesis test will be. And for an ANOVA test, one-way ANOVA test, we're comparing means. So our alternative hypothesis is that all means are equal. So in this case, we have 4 regions, so we have 4 means. The alternative hypothesis is that not all means are equal. And all it takes is one mean out of that whole set to differ just enough to be not equal to any of the others, and then we can say that we would reject the null hypothesis in favor of the alternative hypothesis. It just takes one. So we're going to complete steps 1 and 2 today. We're going to complete step 3 tomorrow. Step 3 is where we determine the actual result of the hypothesis test. Today we're just coming up with the values we need to evaluate that hypothesis test. So we're just going to focus on steps 1 and 2. Step 1, we independently and randomly take samples of households in the 4 U.S. regions. Step 2, we compute the mean energy consumptions of the 4 samples, and then we will stop there today, and we will finish this off tomorrow with step 3. So here is our sample data. We have the Northeast to Midwest to South, and we have the data is presented to the nearest 10 million BTUs. So there's the Northeast, there's the Midwest, the South, and the West. Like I said before, using Google Sheets will make this a whole lot easier. So I'm going to go ahead and jump over to Google Sheets real quick and do some quick calculations that we should already know how to do. You can see that we have our data is right here in this chart up in the top left. And then I've created these new columns and rows down here below that chart where we have our 4 samples. I've created these 3 new rows: the total sample sum, the total sample size, the total sample mean. And then I have these headers in these columns right through here. I have the size of the sample, the mean of the sample, the total number of populations, the sample variance, SSTR, MSTR, SSE, MSE, and F. We are going to go ahead and calculate everything that I've kind of highlighted right there, because those are things that we know how to calculate already. The SSTR, MSTR, SSE, MSE, and F will come as we go through these notes. So the first thing that we want to look at is the size of each individual sample. So for the Northeast, we look up there and we see that we have 5 samples for the Northeast. For the Midwest, we have 6. For the South, we have 4. And for the West, we have 5. We can also calculate the mean for each one of these samples, and that's just simply by typing in equals average, highlight the data in the Northeast column, do it again for the Midwest. So it's average, highlight all the values in the Midwest. Then we do it for the South, average values, and then finally for the West. And we have all of the means of each individual sample. We also know that we're looking at 4 populations, so that's easy to figure out. And then the last one here that we're going to compute in this particular part of the table is the variance. The variance is the difference in the means quantity squared divided by the sample size minus 1. And you don't want to do that for each individual sample. So Google Sheets does make that easy. You just type in equals VAR dot S because we're doing a sample variance. And then in parentheses, highlight the values for the Northeast. We do it again for the Midwest, so VAR dot S. Do it for the South, VAR dot S. And then finally for the West. And we see 3.7 for the West. So there's all of our variance values for each individual sample. The last three values that we can quickly compute are the sample sum, the sample size, and the sample mean. The sample sum is just the sum of all of the sample values combined. The total sample size is the sum of the size of each individual sample. And then the total sample mean is going to be found by taking the total sample sum divided by the total sample size, and we get 9.8. So there's all the values that we need that will allow us to go ahead and complete the remaining part of the table, the SSTR, MSTR, SSE, MSE, and F. It's a lot, but we'll get through it. All right, so these values right here in the middle of your screen, K equals 4, that's the populations. We computed that. N equals 20, we computed that. X bar is the total sample mean, which is 9.8, which we also have already computed. So the next thing that we have to compute in order to build up the rest of the table is the SSTR. And the SSTR, you can see right here, is the sample size for population 1 times the mean of population 1 minus the total mean, quantity squared, plus the sample size of population 2 times the sample mean of population 2 minus the total mean, quantity squared. We repeat that for the other two samples. We add them all together, and we should get 105.9. So on Google Sheets, the way we do this is we will go to the sample size. So SSTR for the Northeast is equal to the sample size times parentheses the sample mean minus the total mean, quantity squared. And we repeat that on down the line. Sample size times sample mean minus total mean, quantity squared. Mean minus mean, quantity squared. Minus mean, quantity squared. So we found all the individual SSTR values for these four samples. The last thing we want to do is add those values together, and we get 105.9. We need that value to go on and compute MSTR, and we're going to look at that here on the notes. So MSTR is right here. It's going to be the SSTR, that's the value we just computed, divided by the number of populations minus 1. So in our case, 4 minus 1. So we'll go back over to Google Sheets. MSTR is going to be equal to the total SSTR divided by population size minus 1. We'll get 35.3. The next value that we want to compute is SSE. And SSE is the individual sample size minus 1 times its variance, and we're going to add all those together throughout the list. So we go back over to Google Sheets. In trouble today, guys. Do it again. All right, so this is going to be equal to the sample size minus 1 times the variance. Sample size minus 1 times the variance. we just do that for all 4. And we're going to sum this column as well. So we take all the SSE values, add them together, and we get 89.3. And you look at our notes, that's exactly the same value we have there. The next one that we want to calculate is the MSE. So the MSE is the SSE, that was the previously computed value, divided by the number of samples, or the number of observations, minus the total number of populations. So in our case, SSE over 20 minus 4. And I'm going to go back to Google Sheets. So it's SSE divided by sample size minus populations. We get 5.58125. Now that is slightly different than what's on the notes. And that could be attributed to the fact that when I did the notes, I used a calculator and I rounded as I went. With Google Sheets, this just keeps using exact values over and over and over. So that could just be a rounding error. We're not going to worry about that too much. So we get 5.81, or in our case 5.85 on Google Sheets. What we're interested in now, though, is finding the value for F. And F is MSTR divided by MSE. Back to Google Sheets. So we get equals MSTR divided by MSE, 6.3247. That is exactly the same value that we have here, 6.32. So there's our value for our F statistic. And that is important in the hypothesis test. And we're going to see that, like I said, tomorrow. Today, I just really want you to focus on being able to use Google Sheets to compute these values. So be very methodical with how you set them up. I'm going to give you 2 homework problems, very similar to what we just did. And that way you can get some practice with it and set up your Google Sheet. So for today, I want you guys to do question number 1, and I want you to do question number 3. And those are going to be your 2 homework questions. So set up your samples in the chart, kind of the way that I did here in this top left, and then create your columns and headers. Make sure you sum up the SSTR and the SSE so that you can calculate the MSTR and the MSE, and then you can set up your F statistics. So as long as you're very careful about how you do these, this shouldn't be too bad. If you guys have any questions, you know how to reach me. I need to go get ready because I've got to be at the high school for graduation from 12 to 4 today, and I hope to talk to you guys soon. So everybody take care, and maybe I'll get lucky and see a few of you this week.